Hello, class 11th physics, chapter gravitation. Today's topic is satellite. What is a satellite? Well, casually we can say a body that revolves around a planet. But to be more precise, we can say a body revolving around a planet under the gravitational effect of that planet in a well-defined orbit is called a satellite. So it must uh, revolve around the planet, and that's too under the gravitational effect of that planet. And also it should revolve in a well defined orbit. So mm, these are the fundamental conditions for a body to be called a satellite. So generally we classify since our childhood we have classified satellites into two categories: natural satellite and artificial satellites. And see, there are so many categories of these satellites, like military satellite and some environmental study satellite and communication satellite and so many different other categories. But generally we divide these artificial satellites into two categories: one, polar satellite, I will tell you about it later, and second one, equatorial satellite. And also we can classify it into three categories. Once again, I will describe these things later, but this is a brief introduction: LEO, MEO, and GEO. Low Earth orbit, low Earth orbit, medium Earth orbit, and geosynchronous Earth orbit. Low Earth orbit, actually exactly from 160 kilometer altitude from surface of Earth to 2000 kilometer, but I am in terms of just in terms of hundreds, we can say 100 kilometer. Actually it is 160, but I am taking an approximation. So many of the observer we which will try to google it will find some orbits ranging from 140, 150, 160. This is just an approximation. 100 kilometer, I mean not less than this, exactly not less than this, and somewhere around 2000 kilometer. It's a huge distance, but not huge enough to be compared with the Earth's radius. Second, medium Earth orbit. Its height, I mean height from the surface of Earth, ranges from exactly this 2000 kilometer to a wide range 36,000 kilometer. And geosynchronous, it is a little bit above this, but yeah, huge gap is there also, which is 36,000 kilometer to 42,000 kilometer. So a wide range of these satellites. The question is how much fuel a satellite requires to orbit around the Earth or a planet. How much fuel it requires. So, and other thing, can we have a satellite set in an orbit uh, having variable velocities? Means, can we, if require, speed up a satellite or slow down a satellite? Is it in our hands? So there are so many questions like this, and see, I'm not going to teach you about Earth's satellites, Indian space programs, and all that. So I'm going into pure physics and just the physical physics related to class 11th only. So let's proceed. But before that, I want to tell you that when a satellite is launched, actually, it begins with launching of a satellite. So, launching of a satellite. So, what is launching of a satellite? We have to take a satellite away from the earth and then we situate it somewhere in a, an orbit uh, where it is supposed to be established as per our requirement. So launching of a satellite, remember we had earlier discussed about the concept of escape speed. We are not going to give escape speed to a satellite, otherwise it will escape from Earth's gravitational field. How can we then be able to take services from that? So just once again I repeat, escape speed is a different idea. It is just a concept to that how much speed is required to escape from the Earth's gravitational field. It is just that. Launching of a satellite requires an idea, like if this is Earth and let us suppose there is a tall tower, tall enough, in fact this much tall. Now see, let us suppose from this height, if I drop an object, and yeah, of course, neglect air resistance. This is something which is very difficult to accept, but yeah, of course, neglect air resistance. And if we drop it, it will directly drop down. Second case, if we throw it horizontally, now there are some cases possible here. First case, it might go like this, like we studied in projectile motion, that if you throw something horizontally, you have studied that from ground projection. All right, one more thing here, I'm not going to make you write notes. If you want to write, you can write it in your own words by pausing the video, but of course few things else I will talk, so don't try to quote everything. Just pick whatever is required to explain launching of satellite. So uh, like projectile motion, we know if we project something at an angle, so it will follow a curved path. And similarly, if we throw this object horizontally, it also follows a curved path. This is projectile motion. Now, um, so same thing will happen here. But what if, what if we give, we increase the speed? Then it might fall somewhere here. It might fall somewhere here. But there is a condition when it will never come back on Earth and start orbiting. So, so this is the choice of a speed, a particular speed we have to give, and that is called orbital speed. Most of the time, I misspell it. I take it wrong. Its wrong name. That is orbital velocity. Sometime I would say velocity, but it is orbital speed. So orbital speed, if we give it orbital speed, that is a prescribed speed at that much height, then it will start orbiting the earth or whatever the planet. So we have to choose that orbital speed. So we have to take a satellite to a certain height and then project it horizontally with orbital speed. So it will start orbiting the planet. This is the idea of, this is the principle behind launching of a satellite, or we can say idea behind launching of a satellite. Now, what if this speed is slightly less? If it is less, then this path will be followed. This is definitely, if that this is a specific velocity by which it will perform circular motion, but here it is less than v naught. But I am talking about if v is slightly less than v naught, then what will happen? If it is slightly less than v naught, then very interesting thing happens. Its orbit becomes elliptical. This is ellipse. Well, it looks like circle because I have made a smaller diagram, but it is an ellipse, somewhat pressed from the sidewise. And what if it is given slightly greater? This one is the case. If it is slightly greater than v naught, then its orbit will become bit elongated. This is, and what if v is effectively very greater than v naught? Then it will go into outer space, and this is a hyperbolic path. So many things are here. I can summarize these. So as you can see here, it will just dropped when this one is when v is equal to 0. This one is when v is less than v naught. This one when v is well, this is not the sign, but I am writing it like this. Understand, I am not going to write slightly, but that is why I have derived this symbol, slightly less than v naught. Then it will follow an elliptic path. And if v is equal to v naught, then we have this circular orbit. And v is slightly greater than v naught, then we will have this orbit. And if v is effectively greater than v naught, then we have this hyperbolic orbit. Well, these are just the concept I'm taking to draw your interest. Otherwise, we will stick to this path only, the circular orbit. So next concept is orbital speed, which we can define the speed of a satellite. Right now we are talking about satellite. That is why I'm just calling it speed of a satellite. Otherwise, it can be of anything which revolves around anything. The speed of a satellite by which it revolves around a planet. All right, so if we take the case of Earth, this is the Earth, this is its radius r, mass m, and from the surface of Earth there is h height, and together this r plus h will refer as small r. So it is orbiting around the Earth, and that satellite has mass m, it has velocity VO, that is orbital velocity, actually our orbital speed, to be more precise. So we know that for circular motion, in order to perform circular motion, we require centripetal force, which is given by gravitational force. So centripetal force is mv square upon r, and VO actually, and gravitational gmm upon r square. R will get cancelled, so it will be mvo square equal to gmm upon r. We will make use of it for another topic. So and from here another topic will go this way. So I have to end this derivation somewhere here. So mm will also get cancelled. So finally it will be v naught square is equal to mm are cancelled now, so it is root of gm upon r. Oh sorry, actually v square equal to gm upon r, and then we will take root both side, so that is why v naught equal to root gm upon r. Now we know that gm is equal to gr square, so we can put it here. So it will be v naught equal to root gr square by r. See, both are different. One is this and other one is this. So we can leave it as it is, no problem with that. And now what I am doing, we know v naught, we have two formulae for that. One is gm upon r and other is gr square upon r. And we know that this small r equal to capital R plus h. So this can also be modified. Actually, I am proceeding it here. So you can do it separately, that proceeding this formula further. Then you can do this. And here again after leaving this, again you can start and forming formula for this. So gm upon this is r plus h, and here if we continue from here, so it will be gr square by r plus h. Now let us suppose satellite is very close to Earth. If satellite is very close to Earth, That is, if we are talking about Leo, Leo satellites. These are Leo satellites, 100 to 2000 kilometer radius and orbit altitude above the Earth's surface. This is the value of H, and the radius of Earth is 6400 kilometer. So you can see how much small value it is. So actually it is almost comparable, but if we go less than that, then such values, even 200, 300, so these are very small values. So these one are very close to Earth. So case we can say that R plus H is approximately equal to R. We can neglect that H, and therefore these formulae will actually, I mean, we are neglecting H, so then V naught for Leo, or very close to Earth. Actually this is much easier to write. Otherwise you can put another subscript that very close to Earth, very close to Earth, a new type of short form it is. So that will be now root gm upon r, or gr square upon r. R will get cancelled, that is root gr. But this is true for very close to Earth, those satellites which are very close to Earth. Well, let's talk about expression for energy associated with the satellite. So first we will talk about kinetic energy, and for kinetic energy we have well known formula half mv square. Right now we will put v naught, and see if such thing is asked, if directly asked in the exam, that derived the formula for kinetic energy of orbiting satellite, then you will start from here, then this, and then you will come to this way. If orbital speed derivation is asked, you have to go that way, and that's true if they ask to derive it for a satellite very close to Earth, then only you need to do it like this way. I mean, proceed it to next step. Otherwise, not required. This step is not required. This step is only required when they ask to find it for very close to Earth. All right, so now half mv square exact value, actually what we can do, we can this put this value also here, squaring it, but when we have entire mv square here, so why will we go with that way? So this will be gmm upon r, that's all, derived. Equation 1, I have to put equation 1. Now we have to find gravitational potential energy. Potential energy, it also contains potential energy, and see, we have earlier derived such formula in my other videos. You can go and check that. So for potential energy we have now this expression, minus g m1 m2 upon r. So here minus, because that in gravitational force is attractive force, and potential energy associated with attractive force is negative, and also negative potential energy explains that the system is bounded to the major system, major one. I mean, both are bounded to each other. So now minus g m1 is m, m2 is m upon r. This is potential energy. Equation 2. So total energy of satellite E equal to kinetic energy plus potential energy. So E equal to half g m upon r minus g m upon r. For sake of simplicity, I am putting 1 g m upon r. Now half of this quantity minus 1 of this quantity means half minus 1, that is minus half of this quantity g m upon r. That's all. Interesting thing is that if let us suppose if kinetic energy of satellite is x, then potential energy, first thing, it is double of that and with the negative sign, minus 2x, and total energy is negative of kinetic energy. That's all. Graph for both kinetic and potential energy will be alike if it is kinetic energy, because it is in positive, so that is why we'll draw it in positive direction. So this is kinetic energy graph. Actually, with respect to r, it is inversely proportional graph, and inverse proportion graph goes like this. Neither they touch this axis nor they touch this axis. Why is it? Think about it. It is totally mathematical reasoning behind this. So kinetic energy, which is positive always, will go like this. And in the same way, the total energy is there. The same graph for total energy, which will go like this, and that's too in negative direction because its expression is negative. E. And also in the same quadrant, we will have graph for potential energy, U, denoted by U. Actually, potential energy I have written PE, but scientifically we have to use alphabet U for that. So U, it is bit more than total energy, so graph will go like this. That's all. Sometimes these graphs are also asked in the exam. All of them are inverse proportion graph, and this graph refers to kinetic energy, this graph refers to total energy, this graph refers to potential energy. Now next is time period. Now what is time period? So it is the time taken by satellite to complete one revolution. Time taken by satellite to make one round trip around the planet. Is called time period. So how can we calculate time period? Very simple formula for that. So that is, we know time equal to distance upon speed. So time equal to distance traveled in 1 round trip upon, and by which speed it will move, distance upon speed, which speed. So satellite will move with orbital speed v naught. So how much is the distance traveled in one round trip? round हो गया ये तो, ROUND, oh hell, round trip. So it is 2 pi r. This is the distance traveled for round trip upon v naught, and we know that v naught is okay. So this root r will go up. There will be 2 pi r root r upon root g m. That's all. This is the formula. Looking quite unnatural one, but of course this is the formula. And see, knowing this, we can calculate that after how much time that satellite will come back. If you people have watched the movie Parmanu, so in that movie they said that they were planning to hide their project from US satellite. So they had calculated time of its orbiting, and by uh, seeing that blind spot uh, during which it was on other side, so they were performing their works. So a very nice movie, scientific one, must watch. Anyway, I have not endorsed for it, but sometimes these kind of things give us a little bit boost. All right, so this is all of it. Further, what we can do, gm, we can put gm equal to gr square, again that thing, but I have a different plan. I'm squaring it. So t square will be equal to 4 pi square, this will be r square, and their root will get cancelled, r upon gm. So finally it will be 4 pi square, actually root will get cancelled when we square it, gm r cube. So it is t square proportional to r cube. Much better, much easier to understand. And for that formula, this is the one thing. Also we can do it like this: t equal to 2 pi r. R has 1 power and root means half power. So 1 plus half, 3 by 2. So 2 pi r 3 by 2 power upon root gm. And also we can proceed it like 2 pi r plus h power 3 by 2 upon root gm. And further we can put t equal to 2 pi r plus h 3 by 2. See, now actually main formula is this, and further we can put the values and change its change the look of that expression. So now we can put gr square in place of that, and that's all. If that satellite is of Leo category, then for Leo, r plus h is approximated to r, then t is equal to 2 pi r cube, then there is no r plus h, r3 by 2 upon root of gr square, that is 2 pi r to the power 3 by 2 upon root g r separate. So finally it will be 2 pi, it will be r to the power 1 by 2, so it will look like r by g. It is more looking like expression for time period of simple pendulum, but it is not that. It is for Leo. Alright, so in this question, find orbital speed of a satellite of mass 8000 kg at an altitude 600 km. So we know the formula, VO equal to root gm upon r. So g, gravitational constant, m mass of earth. So actually this value is given here to misguide you. Actually mass of satellite is not included in the formula. So this velocity is same for all the satellite irrespective of their masses. It depends upon radius, r, radius of orbit. So this r is itself include, r itself include r plus h, radius of earth, and height, or we can say altitude of that satellite. So this is the value of 600 kilometer for h. R is actually 6400 kilometer, which is much greater than this h. So we can ignore this value, or in fact if we include it and make r as 7000 kilometer, so in terms of meter it will be this 7 million, that is 7 into 10 to the power 6 meter. The same question you can solve by taking r only. So we will do both. First we will not ignore h, and later we will ignore h. So this will give us the values 6.67 into 10 to the power minus 11, m is 6 into 10 to the power 24 mass of earth, and upon r, right now I'm using this value 7 into 10 to the power 6. So if we find approximate calculation, it will be somewhere close to, actually we can approximate these values to 7, close to 7, but remember I have increased this value, so final value I have to decrease. So this is approximately, I'm cancelling this. In the exam or in your school you don't have to show this part of calculation, but I'm do it in rough and directly put the value here. So 7 ones are 7, I'm taking it approximately to 7, so 7 ones are 7, that has been cancelled. Only 6 is there. Root of 6 is approximately 2.4. Why is it so? Because root 6 we can write it like 600 by 100. 600, 625, it is close to 625, which is the root of 25, or 576, which is the root of 24. And as I told you, here I increased this value in approximation to make it 7 and get cancelled. So here, in order to take root of this, I have to decrease its value. So that is why I will approach this. So it will be 24 and 100, root of 100 is 10, so it will be 2.4. And then there will be 10 to the power minus 11 plus 23, that is 13, and then 6 more subtracted from that, so 10 to the power 7 is there. Now 2.4, 10 to the power 7, difficult to solve, we can do it like this. And this is 2.4, root 10 into root of 10 to the power 6, its root will be 10 to the power 3. Root 10, remember root 10 is approximately 3.16, 3.16 actually, it is close to pi. Remember these values, otherwise you can even calculate it, but it is better to memorize these values. So it is 2.4 into 3.14 into 10 to the power 3. Again, is there any other calculation? Yeah, approximation? Yeah, of course. 24 3s are, don't know. Then do 12 6s are, half of this and double of this. 12 6s are 72. Leave this part. 72 and little bit more because of this 73 or 74 and one decimal place into 10 to the power 3 meter per second. That's all. The real answer will be close about this, little bit less than this or little bit more than this, but there I guarantee you there will be no huge difference, like and I'm sure it will be not less than 7.2 or not more than 7.8. You'll get the marks for this approximation. In fact, if you would use this fact, ignoring h for Leo, because as I told you it is not a big distance, then V naught will be equal to root gm upon capital R at that, in that case. So g, once again, 6.67 into 10 to the power minus 11 into 6 into 10 to the power 24 and upon 6.4 into 10 to the power 6. I have approximated it to R, ignoring h. Now what will we do now? One's a little bit more than 1. Yeah, of course, little bit more than 1. So we can say 1.05 something, and if we multiply it with 6 it will be 6.3 something. So approximately it will be get cancelled by 1.05 approximately, and multiplying by 6 it will be 6.3, and root of 6.3, with the help of this approximation, 6.3 can be taken as 625 by 100. So approximately it will be 6.3. 6.3 can be approximated to 630 upon 100. Root of this, approximate this as 625, so it is 25 upon 10, that is 2.5. 2.5 into, and what happened earlier, same will happen here, so I'm just copying it. 10 to the power 6 into 10. So it is 2.5 into 3.14 into 10 to the power 3. Multiply this. So once again, 25 3s are 75 and a little bit more than that, 7.6 or 77.7 into 10 to the power 3 meter per second. So there's not a big difference between both of these values. If we convert both of them into order of magnitude, so this will also be 10 to the power 4, this is also 10 to the power 4. So that is why there's an approximation, and we can assume approximately both are same. So that is why it is better to ignore these smaller heights. Now find approximate altitude of geostationary satellite. So if this is Earth, Earth revolves or rotates about its axis from west to east. If in the same way and with same rotation rate, having same time period, we have a satellite in equatorial plane, then what will happen? It will look stationary over this, because when Earth will rotate and this point will come there, so this will be also go that side. So geostationary means the satellite which looks stationary. That is why for geostationary satellite time period is 24 hour, and in one day 24 hour can be converted into seconds. It is we can calculate it 24 into 16 to 60 second. You can remember that this value is 86400 second, or you can calculate it, not a big deal. But the problem is with the formula. We know that t equal to 2 pi by root gm r to the power 3 by 2, which is very very difficult to calculate, and therefore what we can do, we can square entire it. T square equal to 4 pi square upon gm, and here we have r cube, and then we can take cube root of it. So first we'll multiply gm upon 4 pi square equal to r cube. So afterward r cube equal to, r equal to directly cube root of t square gm upon 4 pi square, which is going to be very very which will require rigorous calculation, extremely difficult calculation here. But once again I will go with that approximate calculations, and you can cross check it. Okay, here we can write it 8.6 into 10 to the power 4. So 8.6 into 8.6 into 10 to the power 4 and square of it, so 10 to the power 8. G 6.67 into 10 to the power minus 11. It is better, student, that you take the multiplication of both G and M and memorize that value. That will be much beneficial for you people. Or we can calculate and I will tell you about. I will let you know what is its value, and you can memorize that. Pi square, approximately you can take it to 10. Actually, pi square, value of pi square is 9.86, which is quite close to 10. All right, so everything is set, and see, the biggest problem is this cube root. So we have to arrange the things in a way so that we can easily find this cube root. So is there any way? Let's see. uh, we have to make triplets, and if if we could able to find them, it will be easier. So see now what I'm doing. Once again, a tricky way to find to solve such type of problem with some approximation. At least 5% error will be there. So I'm increasing this and decreasing this. I'm making it 9 and decreasing it to 8 into. Now here, can we do something for this? 4 is in the denominator. If we cancel this and this both, this will be 3.3, this will be 3. So 3 into 3.3, what will be the answer? 9.9. It will be 9.9. See, 4 tens are 40. It is approximately 7. 7 6 are 42. So they are getting cancelled. Not in actual calculation, but approximately they are close. This and this. What else is there? 10 to the power 8 minus 11 plus 24. And cube root of all of it. 9 8 is 72. Cube root of 72. Oh, we'll think about it later on. But here, the blunder will go with this. It is 13 and 8. 13, actually 11. Minus 11 plus 24, or 24 minus 11 is 13. 13 and 8, 21. It is 21. So not a big trouble with this. The trouble is with these values. So actually cube root of 8 is 2, but what about cube root of 9? So we will be stuck. So 8 9 8 is 72. We know that 64, which is close about 72, 64 cube root of 64 is 4. So 4 point, maybe 4 point something, 4.2 will become out from the cube root, and still cube root is there. So cube root of 10 to the power 21 is 10 to the power 7. How is it so? Find it of your own. No, sorry, it is meter. It is in meters. So this value is actually in terms of kilometers. It will be, well, not required, but I want to make you understand what is the value of this entire quantity. I will divide it by 1000 so that it will be get converted into kilometers. So it will be 4.2 into 10 to the power 4 kilometer, which is 42000 kilometer. And see, this is what I told you about GEO. So student, it is nothing like that I am converting these values. Actually, these have come organically, naturally. So you can also do that. And see, the question was approximate altitude, means h, we have to find h. So this r includes r plus h. Here I am doing, actually there is extremely mess up, everything is messed up. So r is r plus h, so h will be r minus r. So r is 42000 minus r is, it is better to use this notation. I mean, we can write it 6.4 into 10 to the power 6 meter, but if it is convenient to use in kilometers, and we can subtract. This time I will not use that approximate calculation. So it is at that much height from the surface of Earth. Now, last thing, find kinetic energy, potential energy, total. Well, if we could find kinetic energy, we can easily find potential energy and total energy, because we know that relation. If kinetic energy is x, then potential energy is minus 2x and total energy is minus x, because of their main formula. So kinetic energy is half gmm upon r, and that is half g. Once again, this thing is coming and annoying us, into m. Oh, sorry, in this question, find, I haven't given mass of, this time mass is required, mass of that satellite. So let us suppose mass is, for the sake of convenience, I'm taking 10,000 kg. Actually, it is a very huge amount, but okay, to make question, we can do that, because I'm fed up of these long calculation now. But you people, you guys, you need to be more active toward calculation. R is what we had okay obtained. So yeah, this one 4.2 into 10 to the power 7. Okay, so now calculation begins. 2 3s are much easier calculation. And what else now? That's all. Okay, is there any approximation I want to do here? No, not exactly. 66 3s are 200, so it is approximately 20. Oh, once again this is 20 upon 4.2. This time I didn't try it, but it happened. 24 4 powers from here and minus 7, so it is minus 18 plus 24 plus 10. So 4 5s are, but not exactly 5, so 4.8 maybe. You can divide it, you can find exact somewhere close to this, into 10 to the power 28 10 joules. Huge amount of energy. And see, we know that potential energy is minus gmm upon r, that is negative of twice of kinetic energy. So we can directly double it, 9.6 into 10 to the power 10 joule. Negative is important, don't miss this. Actually, teacher will get the chance to deduct your marks. And total energy, TE, total energy is equal to minus half gmm upon r, which is same as negative of kinetic energy. So that is equal to minus, again same thing, 4.8 into 10 to the power 10 joule. So that's all, students. That's all for today. And I will upload another video in which some more technical problems based upon gravitation, some more numericals, reasoning questions, conceptual question will be there. So lots of information to come, and I hope you will enjoy it. You will find physics easier, you will find these complicated terms easier with me. Bye bye.